A very good morning to everyone. This is S. Reshma of 2nd MSc Mathematics from Mahalashmi Women's College of Arts and Science. We are delighted to have you all in this 81st MAHA webinar marathon session, which is organized by our PG Department of Mathematics. Prayer. Prayer is always be our first response to every situation, as there is nothing greater than God who is merciful. Let us start our session with the prayer song with the blessings of Almighty.
ஐந்து கரத்தனை ஆனை முகத்தனை இந்தில் இளம் பிறை பாலும் எயிற்றனை நந்தி மகந்தனை ஞான கொழுந்தினை புரியில் வைத்து அடி போற்றுகின்றேனே.
நமஸ்தேஸ்து மகாமாயே ஸ்ரீபீఠே சுரபூஜிதே சங்கசக்ரகதாஹஸ்தே மகாலக்ஷ்மி நமோஸ்துதே. நமஸ்தே गरुडारूढे कोलासुरभयङ्करी सर्वपापहरे देवी महालक्ष्मी नमोस्तुते. सर्वज्ञे सर्ववरदे सर्वदुष्टभयङ्करी सर्वदुःखहरे देवी महालक्ष्मी नमोस्तुते. सिद्धिबुद्धिप्रदे देवी मुक्तिमुक्तिप्रदायिनी मन्त्रमूर्ते सदा देवी महालक्ष्मी नमोस्तुते.
Now, I would like to call upon P. Sandhya of 2nd MSc Mathematics to deliver a welcome address.
Coming together is beginning. Keeping together is the progress. Working together is a success. A grateful morning to everyone gathered here. On behalf of Mahalashmi Women's College of Arts and Science, I welcome you all for this webinar. I extend my sincere thanks to the management and Principal Dr. R. Kumirini ma'am, Vice Principal Dr. U. Indumati ma'am, and Vice Principal Dr. S. Ramasamy sir for their support and encouragement for organizing this webinar. It's our pleasure to welcome our Honorable Chief Guest, Dr.BIJUMON RAMALAYATHIL sir, Associate Professor and Head PG Department of Mathematics in Mahatma Gandhi College in Kerala. He completed his PhD at University of Calicut in 2010. He has a very strong profile of more than 15 years of experience as a lecturer in Mahatma Gandhi College. He was a member in Academic Council and Board of Studies in UG and PG in Kannur University, and Program Officer of NSS in Mahatma Gandhi College, and Presenter of E-Content Program by CEC of University Grants Commission, scheduled by EMMRC, University of Calicut, and he was author of various textbooks prepared based on the syllabus of Kannur, Calicut, Kerala, and APJ Abdul Kalam Technological University. And he was a member of Kerala Mathematical Association. We are very honored to have you, sir. And once again, I welcome you all for this webinar. Thank you.
Thank you, Sandhya. It's a time for photograph. I request everyone to switch on their video for a memorable photograph of today's session.
Thank you all.
Thank you, everyone. Now I hand over the session to our guest speaker. The session is yours, sir.
Thank you, Ms. Reshma. Thank you for the nice introduction of myself. Very good morning to each and everyone. I am very happy to be with all of you at Mahalashmi Women's College, Chennai. I am very much thankful to the organizers for giving me this wonderful opportunity to interact with your students. And I also specially thank my friend, Ms. Bavitra Manikandan, for introducing my presence in this college. Now, let us come to the session. Today, we discuss Green's theorem and its applications. I know that this group includes postgraduate students, and most of them are familiar with these concepts. But this is a approach to using Green's theorem for evaluating areas also. Actually, Green's theorem is a reversion of the work done by George Green, who was a British mathematical physicist who wrote an essay on the application of mathematical analysis to the theories of electricity and magnetism in 1828. The essay introduced several important concepts, among them a theorem similar to the modern Green's theorem, the idea of potential functions as currently used in physics, and the concept of what are now called Green's functions. Green was the first person to create a mathematical theory of electricity and magnetism, and his theory formed the foundation for the work of other scientists such as James Clerk Maxwell, William Thomson, and others. His work on potential theory ran parallel to that of Carl Friedrich Gauss. You all know Carl Friedrich Gauss. He is known as the Prince of Mathematics. Now we state the Green's theorem. Let R be a simply connected plane region whose boundary is a simple, closed, piecewise smooth curve, C, oriented counterclockwise. Now look into this figure. You can see a region here, R. Obviously, this is a circular region, a circular disk. Okay. And this is bounded by a circle, C. And moreover, an orientation, counterclockwise orientation is given to the circle. Here there is another example. This is a square lamina. R is the square lamina and C is the boundary of that square lamina. An orientation is given to C in such a way that the orientation is counterclockwise. R is another region. Here also there is a curve bounding this R, and here also the orientation is counterclockwise. We are dealing these situations. Counterclockwise direction of C and R is bounded by such curves. Suppose f of xy and g of xy are continuous. See, f of xy means f is a function of two variables, x and y. So the domain of this function f of xy will be a subset of the plane. G of xy is also a function of two variables, so its domain is also a subset of the plane. Here what we do is we take the domain of f and g as R, this R, capital R. Moreover, we assume that f and g are continuous and have continuous first partial derivatives on some open set containing R. Then the Green's theorem says that the circular line integral f of xy dx plus g of xy dy is equal to double integral over R, partial derivative of g with respect to x minus partial derivative of x with respect to y dA. See here, this integral on the left hand side is called the line integral, and this is a line integral on a closed circle. So this is indicated by this symbol, putting a circle on the integral side. The curve need not be always a circle. It may be any simple, closed, piecewise, smooth curve. This must be a closed curve. That means if we start from a point, we will go back to the same point. That is the meaning of the closed curve. Now, the advantage of this Green's theorem is that sometimes evaluating this line integral may be time consuming. At that time, with the use of this Green's theorem, by means of a simple calculation and also using the double integral, it is possible to find the value of this line integral. Similarly, sometimes evaluating the double integral may be a difficult job at that time without finding the double integral, but by evaluating this line integral, we can find the value. That is the advantage of this Green's theorem. But some conditions are there. One condition is that R must be a region bounded by a simple closed curve. And also f and g must have first partial derivative. Now we verify Green's theorem in the plane for the line integral over c, xy plus y square dx plus x square dy, where c is the curve enclosing the region bounded by y equal to x square and y equal to x. Now here, what is the region? The region is bounded by the curve c, where c is the curve along the parabola y equal to x square. This is the parabola y equal to x square, and also along the line y equal to x. Y equal to x is the bisector. Okay, and we can see that by looking into this figure, we can see that this is the region between this line segment and this curve is the region. Okay, and on this curve y equal to x square. If for evaluating the line integral, we need the parameterization of the curve. That is very important. Now, what is the parameterization of this parabola? The parameterization of the parabola is obtained by putting x equal to t. If we put x equal to t, then what happens? Y becomes t square, isn't it? So x equal to t, y equal to t square is the parameterization of this parabola. And also you note that we only consider the portion of this one on the parabola. And what about this point? See, this point is some x equal to t and y equal to t square, isn't it? Because we have taken the parameterization as x equal to t and y equal to t square. So we can see that when we put a t equal to 0, x equal to 0 and y equal to 0, that means t equal to 0 corresponds to this point. Similarly, if we put a t is equal to 1, what happens? We get x equal to 1 and y equal to 1, and that is this point. So we get this point and this point, and if we vary t from 0 to 1, we get various points on this portion of this parabola, and we reach here. Then what happens on this line? On the line y equal to x, the parameterization is given by, if we put x equal to t, then from here we get y equal to t, isn't it? Moreover, when t equal to 1, we are at this point ordered pair 1, 1. And when t equal to 0, we have x equal to 0 and y equal to 0. So we are at this point. So that the parameterization of this line segment from the point ordered pair 1, 1 and ordered pair 0, 0 is x equal to t and y equal to t, where t varies from 1 to 0. T varies from 1 to 0. That is very important. T varies from 1 to 0 is very important. You don't say that t varies from 0 to 1. What is the problem? If we consider t varies from 0 to 1, then we will move from this point to this point. That is wrong, because our orientation is counterclockwise. So this is our orientation. So we have to take t varies from 1 to 0. So this is the parameterization of this curve C, and this parameterization is used for evaluating the line integral. Okay. Now here we have to verify the Green's theorem. That means we have to first find the value of this line integral with the help of this parameterization, and then we have to use the Green's theorem and by evaluating this double integral. Okay, we have to find the value again, and we have to verify that those two values are the same. Let us do that work. I think this parameterization is okay for you. Now, what about this? Here we have some function f and g. Now, what about f and g here? F is this xy plus y square, and g is this x square. Now, we are evaluating the line integral. Line integral have two portions. First one is from OA along the portion of the parabola. Then another one is AO along AO. So we evaluate the line integral in two parts. First one, line integral along OA, and second one, line integral along AO. Now, line integral along OA means we are considering the portion of the parabola, and on the portion of the parabola we have observed that the parameterization is x equal to t and y equal to t square, where t varies between 0 and 1. Okay, so on this curve our x will be t, y will be t square. Okay, we substitute those values here. Now what about dx? X is t, isn't it? So dx by dt is equal to 1, isn't it? So dx is dt. So we put a dt here. Now what about x square? X is t, so x square is t square. Dy, y is t square, so dy is 2t dt. See, dy by dt is 2t, so dy is 2t dt. So we substitute those values here. And moreover, the parameter t from 0 to 1. T varies from 0 to 1. Now this is a very simple integration. We can evaluate this one. This simplifies to t cube dt plus t raised to 4 dt plus 2t cube dt. So this becomes 3t cube. This is t raised to 4. So on integration we get integral of t cube is t raised to 4 by 4. So we get 1 by 4 from here. So we get this 3 by 4. T raised to 5 by 5 gives 1 by 5. So adding we get 19 plus 20. Now we consider the line integral along the line segment AO, and we have observed that along the line segment AO with the endpoints ordered where 1 1 and ordered where 0 0, the parametric equations are x equal to t and y equal to t, where t varies from 1 to 0. Now we put all those values here. We get dx is dt and dy is dt. Substitute all those values here. Okay, then here the value t varies from 1 to 0. You please correct this mistake. So we get on simplification we get this is equal to -1. Actually, this is 1 to 0. Okay, so this is -1. You can also write like this: integral 1 to 0 is equal to negative of integral 0 to 1. Now what we do is we add this 19 by 20 with the -1, and we get the value negative of 1 by 20. This is the value of the line integral. Okay. Now in order to verify Green's theorem, what we do is we also evaluate the double integral. Now see, what is the statement of Green's theorem? Green's theorem states that line integral equal to line integral along a simple closed piecewise smooth curve is double integral over R, partial derivative of g with respect to x minus partial derivative of f with respect to y dA. Now here in this problem we have to identify this region. What is the region? The region is the portion bounded by a portion of the parabola y equal to x square and a portion of the line y equal to x, isn't it? Now, while evaluating the double integral, you all know that in order to evaluate the double integral, we need to identify the region and also express the region in terms of a system of inequalities. So what we are going to do like that. So we take a point ordered by x, y here, isn't it? On this region. Now, what is the freedom for x? The freedom for x is that x may be vary from 0 to x equal to 1. Isn't it? X has the freedom to vary from 0 to 1 because at that time we have the x will vary from here on this region. But at the same time, y has the freedom from the line y equal to x square to y equal to x. Only this freedom y equal to x square to y equal to x. So this is the equation representing the region in terms of the inequality. 0 less than or equal to x less than or equal to 1 and y varies between x square and x. Now with this region of integration, we evaluate the double integral as follows. Double integral of this one. Now what about g? G is x square, f is xy. So partial derivative of x square with respect to x is 2x. Partial derivative of xy with respect to y is here while evaluating the partial derivative, we keep x as a constant and partial derivative of y with respect to y is 1. So we get this x negative from here and derivative of 2y, y square is 2y. So negative is here. So we get a negative 2y. And since the region is from 0 to 1 and y from x square to x, we put all these values here. Here we have to evaluate the inner integral with respect to y for the first time. While evaluating the partial integral with respect to y, we keep x as a constant. And on integration, we get to y. So we get xy minus 2y. The integral of y is y square by 2. And 2 and 2 will be get cancelled. So we get this y square. And the limit of integration is from x square to x. We substitute all those values here. And we put y equal to x so that x into x means x square. Y equal to x square. So we get so on simplification, we get this one. And we ultimately get this value negative 1 by 20. And we have observed that this double integral value and the line integral value are the same. So the Green's theorem is verified. Now we consider another problem in which we do not verify Green's theorem, but we use the Green's theorem to calculate this line integral. Okay, we can see that if we use Green's theorem, the calculation will be a very simple job. So as we are using Green's theorem to evaluate this double integral, instead of evaluating this line integral, what we do is we find the double integral of partial derivative of g with respect to x minus partial derivative of f with respect to y dx dy. Now what is the region R here? R is the region enclosed by the x-axis. This is the x-axis and this is the upper half of the circle. So on this region, you can see that as we have to evaluate this double integral, okay, and instead of when we study double integral, you have studied that sometimes polar coordinates will be helpful if our region will be some circular shape region. This is a semicircular shape region. So we prefer polar coordinates over Cartesian coordinate system. Why? Because if we follow Cartesian coordinate system, our capital R is this upper semicircle. And on this upper semicircle, you can see that x varies from negative a to plus a and y varies from 0 to square root of a square minus x square. So if we follow the Cartesian coordinate system, then the calculation will be a tedious job. And at the same time, if we employ polar coordinate system, then our work will be simplified, as the calculation will be very, very simple, because the calculation will not involve complex integral identities. So we prefer polar coordinates, and on this region, a point is of the form ordered where xy, isn't it? But if we prefer polar coordinates, it will be of the form ordered where r theta, where r varies from, what is r? R is the distance of the point from the origin, isn't it? So r is this distance. And what about r? The value of r will be either 0 or from 0 to maximum value will be a, isn't it? See, the radius varies from the radius of the semicircular disk is a. So if I take any point on this semicircular disk, okay, it's the point will be at a distance from the origin, where the distance will be between 0 and a. And at the same time, what about theta? This theta is the angle made by this line segment with the positive x-axis. So the value of this theta will be from 0 to the maximum value for theta will be pi, isn't it? So if you take a point here, its theta will be between 0 and pi. So that is this one. Our region is this one. Theta varies from 0 to pi, and the radius varies from 0 to a. That means if we take a point ordered where r theta on this semicircular disk, its value r will be from 0 to a, and theta will be from 0 to pi. So we use this one for this double integral. We change this to polar coordinate system. In polar coordinate system, you know that the x is equal to r cos theta, y equal to r sin theta. This is the way the polar coordinates are connected with the Cartesian coordinates. X and y are Cartesian coordinates, and the Cartesian coordinates x and y are connected with the polar coordinates ordered where r theta by means of the equations x equal to r cos theta and y equal to r sin theta. Now we evaluate this integral using the polar coordinates, but at the same time, dear students, you note this point that you don't simply write a dr d theta. There is an r, extra r here, okay, while converting this to polar coordinates. And moreover, our x becomes r cos theta, y becomes r sin theta. There is a typing error here. This is r cos theta. And on simplification, we evaluate integral with respect to r for the first time. The calculation is a very simple job, because you can see that integral r dr becomes r square by 2. So that 2 will be get cancelled, and r square from 0 to a, so that this becomes a square, and there is another a here. So we have a cube comes outside, and this becomes integral cos theta plus sin theta d theta. Integral of cos theta is sin theta. Integral of sin theta is negative cos theta. On simplification, we get the value 0. That means we have evaluated this line integral using Green's theorem. Now we use the Green's theorem to evaluate this line integral, where C is this triangle with vertices 0, 0, 1, 0, and 1, 1. Here also you note the point that the advantage of this Green's theorem is that if we use Green's theorem, work will be simplified. Otherwise, what is the problem? We have to evaluate the line integral along this line segment, one job. Another job is evaluate the line integral along this line segment. Another job is evaluate the line integral along this line segment. Okay, so we have to use Green's theorem here. So if we use the Green's theorem, work will be simplified. And in order to use this Green's theorem, we note that on the region R is the region enclosed by these two lines. Okay, triangular lamina. On this point, on this region, if you take a point ordered by xy, x will be from 0 to 1. X varies from 0 to 1. And at the same time, y varies from 0 to x. Y varies from 0 to x. Because this is the line joining 0, 0 and ordered where 1, 1. And the line passing through ordered where 0, 0 and ordered where 1, 1 is the line y equal to x. So the y value varies from this line to this line. What about this line? This is the line x-axis, and on x-axis y value is 0, and on this line y value is x. So we have the system of inequalities, this one. 0 less than or equal to x less than or equal to 1, and 0 less than or equal to y less than or equal to x. So we substitute those values here and simplifies this value to 1 by 2. Here we prefer Cartesian coordinates, don't use polar coordinate system, because polar coordinate system, if we use polar coordinate system, the things will get complicated. In this situation, we prefer Cartesian coordinate system while evaluating the double integral, but here we prefer polar coordinates because our region is of a semicircular portion. Now we consider another example in which also we see that Green's theorem will be very, very helpful, because in order to this line integral where C is the square with the vertices 0, 0, pi 0, pi pi and 0 pi. Okay, if we find the value of this line integral directly, we have to find the line integral along this line segment plus along this line segment plus integral along this line segment plus integral along this line segment. That means 4 steps are required. But if we use Green's theorem, we have to evaluate the double integral of partial derivative of g with respect to x minus partial derivative of f with respect to y dx dy, where capital R is the region enclosed by this square, isn't it? That is this region, And on this region, if you take a point ordered by xy, the point x will be from 0 to pi, and y also will be from 0 to pi, because y has the freedom. Y may be any point here. Ordered by xy may be any point here. So x varies from 0 to pi and y varies from 0 to pi. So we use that one. This is the system of inequalities, identifying a point on this region. We evaluate the partial derivatives, and on substitution we get this value pi square. See, you can see that partial derivatives are evaluated and substituted here. Okay, we evaluate the integration with respect to x, integration with respect to y for the first time. Okay, we evaluate the value, then we evaluate the integral with respect to x, and the final value is pi square. Now we use Green's theorem to evaluate the line integral, where the line is the curve C, where C is the unit circle oriented counterclockwise. Students, though I have used the term line integral for this term, actually the line, the curve C need not be a line, as we have seen in the previous examples. This C need not be a line. Sometimes it will be a curve. Yeah, here the curve is the unit circle. Okay, though this is called line integral, the curve need not be a line integral. The curve need not be a line. The curve may be any curve other than line, as we have seen in this example. In this present problem also, we prefer Green's theorem because calculation will be very, very simple. You can see that partial derivative of g is this x, with respect to x is 1, and partial derivative of f with respect to y is 1, so that the difference is 0. So the double integral value will be 0. So the line integral value is 0. Okay. Now we discuss the physical application of this Green's theorem. For that purpose, we consider the flow integral. In vector calculus, we have seen that a point is represented as a not as an ordered pair x of t, y of t. We prefer it to represent it in terms of a vector. Okay. Now this is called a vector valued function. This is a vector. Why? See, this r of t equal to x of ti plus y of tj is not a vector. Actually, it is a vector valued function. Why? See, dear students, please note that a vector means, for example, if you take a point, if you take a vector 2i plus 3j, it is a vector, isn't it? At the same time, if you consider some ti plus t square j, okay, it is not a function, it is not a vector in general. Why? It becomes a vector when we put a value for t. For example, if we put a t equal to 1, then it becomes 1i plus 1 square j, which gives the vector I plus j, isn't it? At the same time, if we give the value t equal to 2, we get 2i plus 2 square j, and like that. That means ti plus t square j becomes a function, okay, is a function, and when we put values for t, we get a different vectors, okay. So this ti plus t square j is called a vector valued function, okay. And you know that in order to define a function, we need a domain, isn't it? We need a domain. Here, the parameter is t. The parameter is t, and usually the parameter t varies over an interval, closed interval ab, and here a less than or equal to t less than or equal to b. See, among the students, I know that there are so many postgraduate students are there among you. So in complex analysis paper, especially, we have to use the line integral frequently. Okay. And in that idea, you need the parameterization of the curve, isn't it? I have made so many videos based on parameterization, and so many videos on vector calculus are available and done by me. And such videos are available in my YouTube channel. If you are interested, you may go through the videos in that YouTube channel. And moreover, you can see so many animations are there, so that you will get the concepts very easily. So here, r of t equal to x of ti plus y of tj, where a less than or equal to t less than or equal to b is a vector valued function, isn't it? Sometimes certain vector valued functions will generate a curve. Certain vector valued functions will generate a curve. For example, you imagine that an ant moves along a table. An ant moves along a table, and ant will trace out a curve, isn't it? Such a curve can be expressed in terms of this vector valued function. You may go through the videos if you are interested. Now, this r of t trace out a curve, okay, and also this is in this figure there is a curve we can see, and that is the semi-circular curve here. You can see, okay, and there is a vector field is also acting on this point. See, you can see so many vectors on this paper. That means at each point hello, ma'am. There was some.
Now it is okay, sir. Yes, you please continue, sir.
Yeah. I think only 1 second was absent. I missed the only for 1 second, I think.
Yes, sir. Yes, sir.
So you, dear students, you please imagine that you have a water hose of this semicircular shape, and water is flowing along this uh, hose. Okay, and we are interested to know.
Excuse me, sir. Your screen sharing is stopped.
Okay, okay. Okay.
Yes, thank you, sir.
Okay. You please imagine that you have a water hose of this shape, and water is flowing on this pipe. Okay, and you are interested to know the flow of the water along this hose. For that purpose, we have to use this one, this line integral. Here you can see that f is a vector valued, f is also a vector valued function. F is also called a vector field. Vector field means at each point ordered by xy, okay, there will be a field. You can see on this figure, you can see at each point there will be a vector field. There is a vector field acting at each point, and you are interested to know the flow of water along this pipe, and for that purpose we use this line integral. And if the value of this line integral is called the flow integral. I have used the idea of the water and a water hose just to give an idea. This application of this one is in magnetism, like that. In physics, so many applications are there for this line integral. And why we consider f dot t? What is t mean? Stands for, this t stands for the unit tangent vector. Unit tangent vector at each point on this semicircular curve, isn't it? Then what we do is, for example, you imagine that you take a point on this semicircular shape. Then you can see that it's a tangential component will be f dot t. Tangential component means the component of the vector field f along the tangent. Then what we do is you consider the tangential component of that vector field, and we integrate such values along this curve. That value is called the flow. Okay, this is called the flow integral. At the same time, if the curve is a closed one, this flow integral has a special name, and that is circulation. See, you see here we have a closed one, and in this case we consider this flow integral as a special name, circulation. Okay, now we consider an example. We find the circulation for the vector field f equal to x minus yi plus xj around the circle r of t equal to cos ti plus sin tj, where 0 less than or equal to t less than or equal to 2 pi. See, dear students, I have made so many videos based on this circulation and line integral, and if you go through the channel, you can see such videos there. You need see this vector field means at each point ordered where xy there is a vector. For example, if you take ordered where 1 1, okay, if you consider a point ordered where 1 1, then at ordered where 1 1 there will be a vector. What will be that vector? 1 minus 1 I plus 1j, that is 0i plus 1j, that is j, vector j. If you take another point ordered where 1 2, the vector at that point will be 1 minus 2, that is negative 1, negative I plus 2j. Okay, so this is the vector field, and we are interested to find the circulation. Circulation means we have to find the integral along the circle, closed one. That is the reason why it is called circulation instead of flow integral. So on the circle, our f will be, what is circle? The parameterization for circle is cos t sin t, where 0 less than or equal to t less than or equal to 2 pi, x equal to cos t and y equal to sin t. Okay, so we substitute x equal to cos t and y equal to sin t, and we get this one. And we have to evaluate the unit tangent vector. For that purpose, we find the dr by dt. So dr by dt is negative sin ti plus cos t j. You just differentiate here with respect to t. We get a derivative of cos t is negative sin t. Derivative of sin t is cos t. So dr by dt is this one. Now what about f dot dr by dt? You just dot product. Find the dot product. Cos t minus sin t dot negative sin t. Cos t into cos t. See, we get this one. And since sin square t plus cos square t is 1, this is 1. So what about sin t cos t? Sin t cos t is 1 by 2 into sin 2t. And on simplification, we get this one. This is a so 2 pi. Now we express this circulation and use the circulation word in Green's theorem. Green's theorem, circulation k component of curl or tangential form. See, you are familiar with this one. Okay. Integral over C f dx plus g dy equal to double integral over partial derivative of g with respect to x minus partial derivative of f with respect to y dx dy. We have seen such one earlier. Instead of f and g, here we have used m and n. That is the only difference. Okay, this is already familiar to you. Okay. Now, what about this one? We have just shown that this one is the counterclockwise circulation. This is the counterclockwise circulation. We have just observed f dot t. And in vector calculus, you will learn that f dot t ds is m dx plus n dy, where f equal to mi plus nj. So this is this one. And also already by Green's theorem, we have this one, isn't it? So this one equal to this one. What about this one? Counterclockwise circulation of the field. What about this one? This is the double integral of this one. Partial derivative of n with respect to x minus partial derivative of n with respect to y has a special name, and it is called the k component of curl of f. K component of curl of f. If you refer vector calculus textbooks, you can see such a term there. So we evaluate the k component of curl of f, and this will be a scalar valued function, and we evaluate the double integral of that scalar valued function over the region capital R, where capital R is the region enclosed by C. The counterclockwise circulation of a vector field f equal to mi plus nj around a simple closed curve C in the plane equals the double integral of k component of curl f over the region R enclosed by C. This is the statement. Now we verify Green's theorem for the vector field f equal to, see, this is a vector field. So this is f of xy equal to x minus yi plus xj, and the region R is bounded by the unit circle R of t equal to cos ti plus sin tj, where 0 less than or equal to t less than or equal to 2 pi. See, students, I think you are all familiar with the idea that this vector valued function trace out a unit circle. I have made an animated video on this area, and in this video you can see that if we put t equal to 0, what happens? R of 0 is cos 0 I plus sin 0 j. What is cos 0? Cos 0 is 1, sin 0 is 0. So R of 0 is I vector. What is I vector? If you plot the I vector on the xy plane, that will be a vector from the point ordered where 0, 0, initial point at ordered where 0, 0, and a terminal point at ordered where 1, 0, isn't it? Suppose you put t equal to pi by 2. What happens? Cos pi by 2 is equal to 0. Sin pi by 2 is 1. So R of pi by 2 is j. What is j? The j vector is a vector that can be plotted on the xy plane in such a way that its initial point is at ordered where 0, 0 and terminal point at ordered where 0, 1. If we put a t equal to pi, what happens? Cos pi becomes -1, sin pi equal to 0. So we get the vector -i. That is the vector corresponds to the point ordered where -1, 0. Likewise, we can see that when t varies from 0 to 2 pi, we get all the points on the unit circle. Okay, you can see a video on parameterization of curves in a plane made by me. Okay, see here m is x minus y, n is x. N is equal to x. Now what about x? X is cos t, y is sin t. So x minus y becomes cos t minus sin t. Okay. What about x? X is cos t. So what about d of x? Dx. Dx will be d of cos t. What is the derivative of cos t? Derivative of cos t is negative sin t. So this becomes negative sin t dt. Similarly, dy is derivative of sin t, that is cos t dt. And we evaluate the partial derivatives like this. So the line integral becomes, putting the parameterization cos t, sin t, etc. We get this one. The parameter t varies from 0 to 2 pi. So we get this value on simplification. This is equal to 2 pi. And at the same time, if we use this double integral, then also we get the value 2 pi. Okay. Now we are going to conclude the session by mentioning one of the applications of Green's theorem. And we will see that the Green's theorem is very helpful to evaluate the area of a region bounded by a simple closed curve C. Area of a region R bounded by a simple closed curve C. Okay. See, if a simple closed curve C in the plane and the region R it encloses satisfy the hypothesis of Green's theorem, the area of R is given by the following Green's theorem area formula. See, Green's theorem area formula is evaluated as follows. In Green's theorem formula, we have integral over C, m dx plus n dy is double integral of partial derivative of n with respect to x minus partial derivative of m with respect to y dx dy. Okay, now we put m equal to 0 here and n equal to x. Then what happens? Then this becomes integral over C x dy. Here this portion becomes 0 and partial derivative of n with respect to x becomes partial derivative of x with respect to x, that is 1. So this becomes integral over C x dy is equal to double integral over R 1 minus 0 dx dy, which is equal to double integral over R dx dy. Double integral over R dx dy. So look here. What about this one? This is the area. In while you have studied a double integral, you have seen that a double integral over R dx dy is the area of the region, isn't it? So from here we can see that area of the region is this one, and that is equal to the circulation of x dy. Okay, so the line integral of x dy along C gives the area of the region R, where C is the simple closed curve enclosing the region R. So this gives a new formula for finding area of the closed region. Now we use this formula to find the area of the region enclosed by the ellipse. X square by a square plus y square by b square is equal to 1. Okay. Now we use this formula, and we note that on this curve, what is the curve? The curve is the ellipse, and the parameterization of ellipse is x equal to a cos t, y equal to b sin t, where 0 less than or equal to t less than or equal to 2 pi. Okay, so we use that idea here, x equal to a cos t. What about the dy? Y is b sin t, so that dy will be b cos t dt. So we substitute these values here, integral from 0 to 2 pi. So AB takes, now it's at cos square t is cos 2t plus 1 by 2 using the trigonometric identities. And we can see that the integral of cos 2t is sine 40 by 4, isn't it? Sine 40 by 4. And as the limits from 0 to 2 pi, that value will be 0. And what about the integral of 1 by 2 then? That is evaluated separately, 1 by 2 AB into integral 0 to 2 pi dt. What is integral 0 to 2 pi dt? That is 2 pi. So 2 and 2 will be get cancelled, and this is equal to pi AB. You all know that the area of this ellipse is pi AB. We get this area using the idea of Green's theorem. Okay, dear students, and I am also very thankful for all the faculty members and students being present here. The idea that is shared by me is not a new one to you, I know, but I tried my level best to convey this idea within 1 hour. And also all supporting videos are available in my YouTube channel, that so many concepts are required to get the idea of Green's theorem. And I also know that your faculty members have delivered such concepts to you very nicely. And I just revised the concepts in this program. That is all. And I also once again thankful to my friend Miss Bhavitra Manikandan, and also all the faculty members, principal of this college. And thank you once again to my dear students and faculty members. Thank you.
Thank you, sir. Really, the session was very informative. Even though it is not a new topic to us, but you have explained the small nuances of the theorem. It is a new one for us today. We have learned, sir. Thank you so much. And also, I would like to say our principal ma'am came in the session in between. She conveyed our wishes and regards to you, sir. Thank you so much, sir.
Okay, thank you, thank you.
Reshma, proceed with the vote of thanks.
Yes. Thanks.
Good morning, everyone. On this pleasant morning, I would like to present the vote of thanks. I thank all the participants and our guests to make this webinar a great success. I extend my heartfelt thanks to our Honorable Chief Dr. BIJUMON RAMALAYATHIL sir for spending your valuable time with us. Today's webinar is very useful to know about the concept of Green's theorem in this plane. We gathered more information about this concept. Thank you for your knowledgeable lecture, sir. I may also like to express our sincere thanks to Chairman Thiru S. Kunjugabadam sir, Managing Director S.K. Tirukumaran sir, and Thiru S.K. Senilkumaran sir for their consent in organizing the webinar. Thank you, sir. And also wish to express my gratitude to our beloved Principal Dr. R. Kumudini ma'am for their support and valuable guidance. Thank you, ma'am. We also thank our Vice Principal Dr. S. Ramasamy sir and Dr. U. Indumadi ma'am for their cooperation. I thank all the Department of HODs and faculties and participants for valuable cooperation for success of webinar. Finally, I extend thanks to organizing committee and technical team.